Hey everybody, this is Mrs. Ellsworth. I want to make sure we're all on the same page. Last week we started the week with a small lab. So I know that several people were gone for things here and there, and anyway, so I want to make sure that we're all on the same page, so you know what to expect. We started the week with a lab that was talking about the acidification of ocean by putting carbon dioxide into water. And so that would help us understand how carbon dioxide can change an acid in the ocean. So this is really acidification of the ocean was my transition for my students to go from climate change to acids and bases. So that was my idea there. So then we did that lab. And then we started the new unit of acids and bases with another quick lab where you were going to do a quick lab, and you got these different results pretty much. And so this right here is a very, very brief thing of what we did in class the last couple days. And so if you were gone, there will be a video that is posted on Google Classroom. Just as soon as I'm done with this video, I'll make sure that it is posted. And that video is how you can get caught up on all of this portion of it. So if you are missing this information, the notes sheets are in the top tray, in that stacked tray over by the classroom door. And so go grab that, and let's go ahead and get started. But those notes, unfortunately, you will have to do on Google Classroom, not right now in class. Okay, so here's a brief reminder of what we did do. Okay, so we talked about properties of different acids and bases. Okay, and that kind of helped prove with what you guys did in that lab. We also reminded ourselves how to name acids and bases. I guess acids with that chart that you drew on your purple polyatomic ion chart. And so then that would help us just figure out how to name these. And so we practiced with a few of those. And then what did we do next? Well, with our notes, we also came up, there's a couple of definitions, and we talked about Arrhenius' definition of acids and bases, and then we briefly touched about the Bronsted-Lowry one. So oopsie, let me get to the right page here. So when we talk about the Arrhenius definition, we would talk about how that it would, I'm going to show something different here real quick. We would talk about how with an acid you would get a hydronium ion, or with a base you would get a hydroxide ion. Okay, and so that's pretty much his definition. But we also learned about the Bronsted-Lowry one, and period 7 will be going into a lot more detail of this because they didn't get very far on this. So with the Bronsted-Lowry one, we talked about how that this acid is donating that hydrogen to become the hydronium ion here. So then you're just left with that chloride that is left here. Anyway, so this right here is really what the basis of the what the Bronsted-Lowry idea is, whether something donates a proton or a hydrogen ion, or whether it accepts it. Okay, but let's talk about briefly about so this is where the two classes change. Period 1 had a little bit of knowledge with the electrolytes here, but I want you to just look at it one more time. And I know that period 1 has these notes for this table here, but period 7 you're going to have to write this table, so you'll have to pause for that. Okay, so let's go ahead and look at the PhET lab simulation. Understanding how molecules and ions react together is such an important part of chemistry. And I like this PhET lab simulation because they are showing right now, I mean, if I showed a pH stick, this would be water. It'd have a pH of 7, which is neutral. Okay, and so the strong acids, the strong bases, they'd have different pHs radiating out from 7, either towards 1 or towards 14. Okay, but what's important here is just looking at the molecules. Okay, if this was a pH of 7, we don't have any kind of acid and base in there, but here, look at that. Remember, water is amphoteric. Water can behave as either an acid or as a base, and when they are in this form, they are in ionic form, so they have a charge to them, and that's what actually allows electricity to go through them. So when we look at this bulb right here, it is barely lit. You can't hardly even see any rays coming out. And when we use a 4-watt white light bulb or a 25-watt light bulb in the classroom, we can't even see on the filament in the light bulb. We can't even see it light at all. Okay, there's not enough electrons going through there to create any light. Okay, so but I see on this program here that they've got a lot of light that is emitting from there. Well, let's go ahead and put all of our water molecules in there. So what happens is that the water molecules are bumping around because we know everything is in a state of motion. It's got kinetic energy. And so what happens is that they bump into each other and they might create these ions, but guess what? They go back into the water form too. So as bumping is happening and going in and out with different molecules around here. Okay, so then we notice that this doesn't have, it's a non-electrolyte because they don't have much light going here. So this is where I want you to go ahead and create this chart and note that water is a non-electrolyte. Okay, so water is a non-electrolyte, and then I want you to also make another note of something else, that this right here was mostly molecules, wasn't it? Okay, I don't know where to write this, so I'm just putting it in here because I got room in this column. You can put yours over here wherever that you need it. Okay, so water's mostly molecules. Molecules don't really conduct electricity. It's the ions that conduct electricity, so that makes sense that a non-electrolyte would be mostly molecules. Okay, let's go back to the app here as you're ready. Okay, so there's water. Let's look at a strong acid. Okay, wow, look at that. Strong acid. The only molecules I see in here are of the solvent. There are none of these molecules. This is what the acid is, and so you go put it into the water and hey, it breaks apart into these ions. Hey, it really breaks into pretty much all ions, doesn't it? When you remove the water, it's almost all ions. Okay, so let's go back to that chart. Oh, I forgot to mention one thing too. Look how bright this is. Let's do a comparison. Okay, not hardly any rays coming off the light bulb, and here there's a ton of them. Okay, so it's very bright. Okay, it's strong electrolyte. Okay, so that's where we're going to put that information, that this is a strong electrolyte. Okay, and this right here is mostly ions. It's mostly ions. Okay. Now let's go back to that app. And so here's what our water looked like up here. Not much. Strong acid. Wow. And then a weak acid. Here it is, not as much. Okay. But it's definitely more than the water, isn't it? And the weak acid, when we do this with a like vinegar in the classroom, that's a weak acid. We barely see the filament light up with a 25-watt light bulb, and you can just barely see it glow in there. And so that's pretty interesting. And so that's, why is that? Well, here I'm going to remove our solvent again. Look at all these acid molecules. Okay, it didn't break apart. Didn't break apart into ions. So this is showing you that there is lots of molecules and ions in here. So it's a mixture of the two. So it didn't fully ionize like the strong acid did, but the weak acid only partially ionized. Okay, so that's a great way to write that down. So let's go back to our chart. So this right here is ions and molecules. Okay, and it was a weak electrolyte. Okay, if you need to pause it, go right ahead. Okay, so let's go ahead and look at a strong base. Okay, strong base, there we are, strong base. Look at that strong electrolyte bulb is really bright there. Just compare it again to the weak acid. Okay, compare it now to the strong acid. Look how bright it is. Strong base, strong acid. It looks like it's about the same here. Look at those ions too. Wow. Anyways, I'm going to remove that solvent so it's a little bit easier to see all of them. Do you see any of these darker gray ones? No. This thing has completely ionized, and that's why it is a strong base. Okay, it is completely ionized, and that's what carries such a strong current, all those ions in there. So that really helps us. It's a strong electrolyte, strong base, strong electrolyte. These are almost all ions. Okay, and the water is just really just a highway for those electrons to bounce from one ion to the next, and so that really helps it conduct the electricity. Can you make a prediction on where the weak base would be? I bet you can, but we're going to do that right now anyway. Okay, so here's a weak base. Ooh, lot less ions in there. Wow, look at that. There's so many molecules of the actual base in there, okay, and there's no charges with that. So that explains why there's fewer of these with a weak base. So there's less electricity that goes through there. Okay, so look at that compared to the weak acid. Okay, notice that there's the acid molecules and then there's the ions there. And notice the brightness is very, very much the same. Okay, so you probably even predicted right that there's a weak one and that they are ions and molecules. Oops. ONS and molecules. Now, what is the big picture? Okay, that's important. What is the big picture of this? Why would I even show you this? I mean, electrolytes, acids, bases, what is the importance of that? Well, it is important to notice that the strength of the acid matters, doesn't it? The strength of the base matters. In fact, you would notice that the two strong ones have more ions to conduct more electricity. Okay, and that the weak ones, they have a mixture. They are only partially ionized. Okay, they're only partially ionized. And so that's what makes them weak, because there's not as many ions in there to conduct the electricity. And then the water has so little ions in it that it can't even conduct electricity enough for us to see. Okay, so that's the big picture of that. Okay, so with that information, we are now caught up to where we need to be for today. I will see you later.